This video is part 2 of the small language we're constructing, and in this video we'll take a look at the parser. And to begin with, we'll need to define a grammar for the language. And what I mean is, it's what types of different expressions there are and how they are related. So hopefully it will make a bit more sense in a minute. A primary type of expression is something that is kind of indivisible in a sense. It's something that is evaluated in the very beginning. So for example, when you look at this expression, a times 2, a and 2 are what is known as primary expressions, and they are a variable and a number. In more complicated languages you might also have things like strings here, but we don't have that because it's just a simple calculator language. Now, another thing we can also have is a parenthetical expression. So there is something that is an expression, which is the top level, and it's consisting of subparts. We'll see what that means in a bit. But a primary thing, this is the thing that's evaluated first. When we evaluate an expression, it can be a variable, it can be a number, or it can be a parenthetical thing, where the thing inside can be anything. Now, another type of expression could be addition, where we have something like this. There's also subtraction, which is quite similar, just has a minus there. But there's two things that's a bit annoying with this, and one is the fact that these are very similar and they are kind of separate. So we can already quite easily join them by saying that we have something called a term, which is two expressions with a plus or minus inside. The reason we need to have expression here on the left and the right is because we need to allow things like 2 plus 2 plus 2 plus 2 and so on. Or let's say minus here and maybe also minus here. So that's implicitly allowed because we have this recursive definition where the term refers back to the top level, which is the expression. We can, however, avoid that if we do the following thing. We say, okay, there's a primary thing, and then there's any number of additional expressions, like that. This star is supposed to mean 0 or 1 or any number, but including 0. So that means that the primary one is actually included. Like if we just have an identifier, it's actually included in this part of the grammar. So we can remove it from up here. This is kind of a nice trick and will let us write a parser in a simple way from just looking at the grammar. Now, this only supports plus and minus, but we actually also have multiplication. So we can call that factor. And it's kind of structured in the same way. And now we can, of course, like on the left hand side of a plus, you can also have something that's multiplied. So we can put factor here. And then we have actually already encoded that factors, things that are multiplied, things that are divided, are calculated before we calculate what the plus or minus result is. The final thing we need to support is expressions like this that are assignments. So let's put an assignment here. It's on the top because it's the thing that's evaluated the last. Whenever you see something like this, right, you will first figure out what the left-hand side is, and then first you'll figure out what the right-hand side is, and then you will assign that to the left-hand side. So the assignment is the thing that happens at the very end. Everything else is evaluated first. So assignment looks like this. It's the way I've chosen to represent it. First, there's a variable and an equal sign. Maybe there is, maybe there's not. Then, instead of having a kind of like a infinite, possibly infinite number of this sub-expression repeated, I just go back to the top. Now that actually allows things like this, and we'll have to discuss how this is evaluated when we run the program. But you can see that that matches the assignment thing, because we have a variable, we have an equal sign, and then we have another expression here. You could disallow it by not having expression here, but I think it's quite nice because sometimes you actually would want to write this. Let's now start the parser. We'll write it here in the main function again to begin with, and later I will move it to a separate module. And a parser is something that takes a list of tokens and returns a list of expressions. So we still haven't defined what an expression is, and we have to use the token type from the token part. Let's also put a to do here so it doesn't complain too much about that. And now let's define what an expression is. The way I usually define these things is to define an enum, and it'll have the possible expressions. So there's a variable expression, and it has some internal data, which I like to put in a separate struct. You can also inline it like this, right? So put some data here or whatever. But for reasons that will become clear in a little bit, I don't like to do that lately. So in that case, it looks like this. Maybe we'll make something called a binary operation that has plus and minus and multiplication and so on. And then we'll also have an assignment. Just for it to look nice, let's put it in alphabetical order, like so. And now these things we need to implement. So assignment implementation. How should that look? Well, it has a target, which is the left-hand side, and that should be a variable. And then it should have a value, which has to be a box of an expression, not like that, but rather like this. We need to box it because it's kind of implicitly referring to itself through this line. And now you can see why I like to have these implementation structs defined separately, because now I can say that an assignment implementation has on the left-hand side as the target always a variable. If we didn't have these separate structures, this would have to be a box expert as well. So that's not so nice. Then let's define the binary operation implementation. It has a left-hand side which is an expression. It has an operation, which we can just represent with a token. And it has a right-hand side. Then there is the number implementation. There we can say it has a value, which is, for now we only allow integers. Also include the token, just because. And then there's the variable implementation, which just has a certain name, which is represented by a token. So that defines the expression enum. And now we just have to write the parser. So what we're going to do is we're going to gradually consume tokens. So I'm actually going to make them mutable, and then I'm going to reverse it so we can, by popping from the back, we can consume them one by one. Then we're going to have this result type vector, which we return in the end. Then we'll just consume tokens until there's nothing left. And now we're going to do something called recursive descent parsing, which basically means we start from the top and we'll say, let's parse an expression, because that's the first level. Parse an expression, and it will have to consume some tokens, so we give it a mutable reference. Then we're gonna say that every expression needs to end with a new line. So we'll have this expect function that will try to get a new line token from the top, and it will panic if it doesn't find it. So if that works, we can push the parsed expression to the results, and then we are done. So let's start, just so we have it, let's start by implementing this guy. So we'll need token type here, and we will need to say that this is actually from that enum. All right, so we'll try to get one. If we don't see anything, we'll say that's okay, it's just the end of the file. That's kind of like an implementation detail, that it's either we get the token we asked for or we get nothing. If there is a token left, then if that token type is not equal to the expected token type, then we'll panic and we'll say expected token got. So we'll have expected and we'll have token type. And otherwise it's fine, we don't do anything. Now there is a small problem, which is that these structures are not equatable yet, so we'll just derive that. Then we'll go back. Okay. So the next thing is to write this function parse expression. So again, we're using this recursive descent pattern. So we'll have some tokens, it's a mutable reference to the tokens, and it should return just an expression. And then we go over here and we look in the grammar and we see that, okay, an expression is an assignment. So that is actually kind of trivial. I keep it anyway, just so we follow this structure of the recursive descent parser fully. So that was that level. So now let's go to the next level, which is a bit more interesting. here we will try to pass an assignment. So first we need to look one ahead, and we'll do like so. We'll take a reference to the last token, and if, sorry, the next to last, we're trying to look ahead to see if there's an equal sign. And if there is that, we'll do something, otherwise we will do something else. So if it is an equal sign, then first we want to get a variable. So we will recurse down, we will consume a variable, we will pass a variable. Then we will say, okay, the next thing has to be an equal sign. And then we need the right-hand side, which can be an expression as we see on the right. And then we are actually done. We can just return an assignment, which has an assignment implementation where the target is this variable and the value is the value. Right, and we need to box it actually, so do like that. Now, if there's no equal sign, then we have to try to pass a term. So we can just say pass term. There's actually another case we didn't consider here, which is what if there's only one token left? So what we can do is we can say, let's say there's more than one token left, and we'll inline this. Then we try to pass a variable. So let's write the pass variable. That is kind of outside this recursive descent thing. And because that should not return an expression, but only something very specific. So let's get a token. We'll assume we can unwrap it. And then we'll have to require that it is an identifier. If it is, we can just return a variable where the name is given by that token. And otherwise, we'll say expected identifier found something else. So now we have pass variable. Now we need to pass a term. Now we're back in this recursive descent pattern. So we'll pass the term, given the tokens. It returns an expression. And we want to pass first a factor. It's going to be mutable, as we'll see in a little bit why that is. If there's any tokens left, then we have to kind of peek at the next token. So if we see a plus or a minus, then we know we're actually in a term. If we see something else, we're gonna break. And the final thing we do down here after all of that is return the result. So what this while loop is supposed to do is to account for this possibly infinite number of of sub plus minus expressions. So let's get the token. Then we can pass the right hand side. It's a factor according to the grammar. And then we can modify the result. We'll make a binary operation, and it should be a binary operation implementation. And the left hand side is the result, previous value of the result boxed. The operation is the operation token, and the right hand side is a box from the right hand side. And if I'm not completely mistaken, that should be it. But there still is some kind of mistake. I guess we have to say that these are token types. And this one has to be a comma. So now we continue in our journey in the recursive descent, and we'll pass a factor. So they all have the same signature. They return expressions. And it looks, again, quite similar. But now we try to pass primary, because it says primary here instead of factor. We'll do the same thing. I almost want to copy paste. There's a reason to have it as separate functions, because it allows us to much more easily handle the operator precedence. In the end, we need to return the result. Okay, so if we have a token type equal to a star, or a token type equal to a slash, then we want to do something. Anything else, we just break. And here we'll again get the operator token. Then we'll pass the right hand side, which is a primary expression. And then we will reassign result to be a binary operation implementation. Left hand side is that, operation is that, and the right hand side is this. The final thing we need now is to pass the primary. Again, it takes some tokens. So let's get the top token. So if we have a number literal, then we want to do one thing. If we have a identifier, do another thing. If we have a left parenthesis, we need to do one more thing, yet another thing. And anything else we actually want to panic, and we'll say unexpected token type. And that is it. This one has to be comma instead. So a number literal is quite easy because we just return a number, which has a number implementation. The value is pass a number from the lexeme, and the token is just a token, and we return that. Then we don't need this. So let's just write this pass number thing real quick. It's gonna return an integer, and if it will assume it always works, so we're just gonna unwrap. This one is also quite easy. If we see just an identifier, we know it's a variable, and the name is given by the token. And this one is a little bit interesting, because if we see a left paren, we actually have to, as you see here, we have to recurse back up to the top and pass a whole other expression. So that's why it's called recursive descent, not just descent. So what we're going to do is we're going to pass a full expression, and then we're going to declare that this expression must be closed with a right parenthesis. And then we can simply return that in the end. So that is it for the parser. And now let's try to see it in action. So let's remove this. Let's get expressions. We're gonna pass the tokens. And then for expression in expressions, we could try to print it. And that's not gonna work because they are not debug printable. And that is actually a bit more work to do. So we'll do that in another video, or I will do it off screen. So for now, let's just check that it actually runs. And it doesn't run. So now we have something that works. It runs. The thing that was missing was just putting in an ampersand in front of this guy, which is a bit weird. But now there's actually one more thing we need to do to make it fully functioning, which is we have to handle function calls. So actually there was a bit of a mistake in our grammar here. It's also possible to have a function call. So let me write it as a separate thing. So this is a variable name, then it's a parenthesis, then it's an expression, then it's another parenthesis. So that is a primary thing because it's evaluated first. Yeah, so let's have a look at that. So if the length of the tokens is greater than 0, there's anything left, then it might be a function call. So let's say next token, we're just gonna get that. Well, actually, because we might not want to consume it, so let's just look at it. And if that next token's token type is equal to a left parenthesis, then we will try to pass a function call. So we already have the, let's say, the function name. That is a variable where the name is given by the first token we found. And I made a bit of a mistake here. And now we need to pass an expression. So first of all, let's remove the left paren. And then let's say arguments is given by passing this sub expression. For now, we'll only allow one single argument to make it easy. So we pass that. Then it should end with the right parenthesis. And then we can finally return a function call, which we haven't implemented yet. But it should have probably a name, which we can say it's the fun name. And it should have an argument, which probably has to be a box. And somehow there is a mistake. All right. So let's add that here. The name is a token and the argument is an expression. Now if we go back, actually, let's go back here. It shouldn't be a token, it should be a variable specifically. And now it should be working. So let's try to run this. And again, it panicked. And it panics here. So let's try to do some live debugging. Trying to pass fun call. And whatever. Let's try to run that. It seems we never hit that point. Let's try to simplify the problem a little bit like this. And that worked without any problem. So now let's try this one. That one panicked. Let's, just for debugging purposes, let's print these guys. So that looks correct. It never goes in here, which is interesting. So it gets an it does pass a primary. Interestingly. Okay, the bug is the following. All these have the same token type, which is wrong. should of course be star here, slash. This is what you get from copy pasting. Left paren, right paren, and new line. That was correct. So now it actually works. Let's remove the print statements. And there we have it. A parser for our small language. And let's try to do this. Maybe we want to know what 2 times 3 is. And that works. So that's the parser. In the next video, we'll make an interpreter that will take these expressions that we made, turn them into values, do the calculations and so on. And then we will have a usable language.